The natural question that comes up in the context of parallel implementation is, can it only be applied in the context of something like an FIR filter, where we can make use of all the equations and the arithmetic that we saw earlier? Or can we generalize this idea to something that can be applied to any kind of data flow graph, which after all, as we saw, was a good way of representing the general dependencies between various tasks that are involved in a certain kind of signal processing computation. As an example, let's take up a simple data flow graph where we have two computational units, A and B. This arrow, of course, indicates that B depends on A, or in other words, only after A has computed, that output is then used to compute the value that is used by B. And in turn, we also have a return edge with two delay elements on it. Now, what does this mean? It basically says that the value of B that is computed in a given iteration is used by the computation of A 2 iterations later. In effect, this is sort of like having an IIR filter where there is a 2 sample delay in what is fed back from B back into A. Now let's consider a situation where the delay of A is some 5 time units. I don't care what the time unit is, it could be nanoseconds, it could be clock cycles. At the end of the day, all that we care about is there is some unit and it is 5 multiples of that are being used in order to finish one computation of A. Similarly, B also takes 5 units. So effectively, in other words, as we see this system over here, one of the things that we can say is we know how to compute the iteration period bound. It's equal to the delay of A plus the delay of B divided by the total number of edges, number of delay elements in the loop A to B to A, which in this case is 5 plus 5 divided by 2, or in other words, the iteration period bound is 5 time units. Ideally, in other words, we should be able to process one sample through this particular data flow graph once in every 5 time units. On the other hand, the critical path of this structure that I have drawn over here essentially goes through the path A to B. And what that means is that the critical path is equal to the delay of A plus the delay of B, which is equal to 10 time units, which means that time per iteration, if I directly implement this way, is going to be 10, which means that the sample interval is also going to be 10 time units. Whereas I would like it to be 5 time units, which is a theoretical best that I can do for this system. The question, of course, is how do I get to that? Now, you would probably have observed that there's a fairly simple way of converting this data flow graph into something that has a critical path of only 5 time units. The method that we can use is retiming, where essentially what we say is I will take this cut set of edges, and by retiming around that, I will get one delay on the edge from A to B and one delay on the edge from B to A. The overall system will have the same behavior as the original, except that the exact timing would be slightly changed. The resulting system, of course, has a critical path equal to 5 time units, which means that the sample interval is also equal to 5 time units. So in other words, we have achieved our ideal sampling rate, sampling interval, which is equal to the iteration period bound, and even theoretically it's not really possible to go any better than this. So it looks as though that's the best that we can achieve, and in fact in this case that is correct. On the other hand, what happens if the delays on my data flow graph were slightly different? In other words, what if I had a system that looked like this? Again, the same connections between the nodes A, B, 2 delays, but now A had a delay of 9 time units and B had 1. The iteration period bound in this case is exactly the same as before. It is 9 plus 1 by 2, or 5 time units. The critical path over here is also equal to the distance from A to B. There is a total time on A to B, which is equal to 10 time units, and the sample interval is equal to 10. Let's apply retiming and we end up with a modified graph which looks like one delay here, one delay here, and here comes the problem. The critical path now is going to be A, which has a delay of 9 time units, which means that the sample interval is equal to 9, which is significantly greater than my ideal sampling interval of 5. In other words, what this is telling us is that when I have a heavily unbalanced system of this sort, no amount of retiming will allow me to solve the problem unless I can somehow go into A and split it up further into smaller segments, which may or may not be possible in practice. The question is, what can I do in such a situation? Is there any way that I can get to a better sampling interval or a better average rate at which I can process samples? And as you might have guessed, the answer of course is yes, you can use the principle of unfolding, which is a form of parallelism in this context, and redraw the data flow graph in a cleaner manner that allows you to exploit this. So in order to appreciate the idea of unfolding, we first need to look a little bit deeper into the idea of token firing sequences that we looked at in the context of data flow graphs. Essentially what we are saying is the node A corresponds to a firing sequence which we will call A0, A1, A2, etc. for node A. And similarly, there is another sequence B0, B1, B2, etc. for node B. Now, the dependencies that we see in the original graph over here before we did the retiming essentially correspond to something like this. B0 depends on A0. In other words, only after A0 has computed, I can then compute B0. Similarly, B1 depends on A1, B2 depends on A2, etc. But what about A1? Does it depend on B0? No, it depends on something which was 2 cycles earlier. Or in other words, another way of drawing this would be to say that A2 depends on B0, A3 depends on B1, A4 depends on B2, A5 depends on B3, and A1 in other words would depend on B minus 1, which we will take as an initial condition and therefore we can sort of ignore for now. So these colored arrows are basically showing us what the dependencies in this firing sequence are and what it is that we actually need to keep in mind when we are implementing this in practice. Now, what does that imply for the data flow graph itself? And is there a way by which I can essentially create 2 parallel copies of this data flow graph that will have the same final result as the original? Let me start by essentially creating 2 copies of the computational nodes themselves. I'll call them A0 and A1, and similarly B0 and B1, right? Effectively, in other words, what I'm saying is that the node A0 is going to compute the iteration values A0, A2, A4, A6 and so on, whereas A1 will compute A1, A3, A5 and so on. And this B0 in turn will compute B0, B2, B4, while B1 will compute B1, B3, B5 and so on. So now how do I use this in order to put the edges between the different nodes that I have over there? Let's write out the firing sequence in a little bit more detail. Effectively what I have in other words is A0, A2, A4 being computed on one node, A1, A3, A5 on another node, B0, B2, B4 on one, and B1, B3, B5 on another. Which means that if I draw the dependencies, I will end up with something like this from A to B, but a slightly shortened set of dependencies, that is to say the B1 to B3, B3 to A5, B1 to A3, B3 to A5, B0 to A2, etc. dependencies are just to the next element in the corresponding A0 chain itself. If I draw the data flow graph corresponding to this, effectively it looks something like this. There is a dependency from A0, the computational node A0 to B0, and there is a single cycle delay element between B0 to A0. Why is that? You can understand that in the context of this diagram that we have over here. Right? This edge essentially corresponds to only a single delay. So then if I go back, I now further have A1 to B1, and that also has a single delay element on it. Effectively, what I have done, in other words, is that I have been able to redraw my original data flow graph, which looked something like this, to a set of two parallel data flow graphs with a single delay each on them. The iteration period bound in this case is, assuming that I still have 9 and 1 as the actual delays on the computational nodes, I have 9 plus 1 by 2 equal to 5. The critical path is equal to 10, which means that my sampling interval is equal to 10. What about on the right hand side? I find that my iteration period bound is actually equal to 9 plus 1 by 1. Right? Note that now I have only one delay element on each of the loops present over here, which means that the iteration period bound is equal to 10. But the interesting thing over here is now the critical path is also determined by these two edges and basically becomes equal to 10, which means that the sampling interval is equal to the critical path divided by the parallelism factor. Why? Because effectively within one sampling interval, two parallel copies of the computation have been performed, which means that the effective sampling interval for the overall system is 5, which matches my original target iteration period bound. Notice that the iteration period bound for my modified parallel graph is actually worse than what it was for the original graph. But because I have the parallelism factor, the sampling interval that I can actually achieve has matched that of the original graph. What happens if we want to draw a slightly more complicated, or rather to unfold a slightly more complicated graph? Let's consider a situation where we again consider the same basic structure, but now with 3 delay elements on it, and I now want to unfold this by a factor of 2. How exactly does this happen? Effectively, the best way to understand this would be to actually draw out the sequence of firing, which would tell us A0, A1, A2, A3, etc. and B0, B1, B2, B3, B4. And what we can see is that there is a dependency from A0 to B0 and then from B0 to A3 in this case, then from A3 to B3, B3 to A6 and so on, right? And similarly there is another dependency that goes from A1 to B1 to A4 and so on, right? Now if I redraw this in terms of my 2 parallel architecture, what I effectively have is, in my 2 parallel architecture, A0, A2, A4, etc. are computed on one node, whereas A1, A3, A5 are computed on another. Similarly, B0, B2, B4 and B1, B3, B5. Now what do the dependencies look like? I have a dependency from A0 to B0, but from B0 to the next one, A3. That is to say, the one delayed version on the second copy of A. Right? So in other words, it's important to understand exactly what this dependency edge implies. This is a one delay on the second parallel copy of A. Drawing this out will probably make it a little bit easier to understand. Effectively, what we have in other words is, I have the two parallel pieces of hardware, A0 and A1, and I similarly have B0 and B1. From A0 there is a direct dependency to B0, but from B0 I need to essentially go to A3, which is a one sample delay on the hardware A1. In other words, it corresponds to one delay element as shown here. Now what about the next edge? From A1 there is a direct dependency to B1, but from B1 what I have is a dependency to A4, which is a two sample delay on A0, which basically corresponds to this edge shown in red, but for now with two sample delay, right? Just as this one sample delay corresponded to this value out here. So this is kind of interesting. What exactly have we got as a result of this unfolding process? We have two copies each of A and B, which implies that the total hardware requirement has essentially gone up by a factor of 2, which is pretty much as expected, because that's what we expect happens when we try to implement in parallel. We are willing to pay the price of extra hardware in order to get better performance. But what's the result? The resulting iteration period bound that I have over here is 2 times the delay on the loop, that is to say dA plus dB, divided by 1 plus 2, the total number of delays, total delay elements in the loop A0, B0, A1, B1, A0, right? Which when I compute turns out to be 2 into 10 by 3 or 20 by 3. This is the iteration period bound of this unfolded structure, which means that the average sample period in turn is going to be equal to 20 by 3 divided by 2 or 10 by 3. That's the best sample period that we can expect to see. What is the practical sampling period? The critical path in this case is of course equal to A0 to B0 or A1 to B1, which is 10, which means that the actual sampling average sampling interval is going to be equal to 10 divided by 2 or is equal to 5, which is closer to 10 by 3 than the original best, which was 10 itself, but has still not done the best possible. So in other words, effectively what we are seeing over here is this example was primarily to show that you don't always have to unfold by a factor which will give you the completely separated out loops. In fact, in some cases it may not even be possible, but in general, by unfolding in this way, you can create a resulting structure which has a better average sample interval than the original structure that you started out with. Unfolding, in other words, can be applied without even needing to know the details of what are the actual computations being performed by the nodes A and B. I don't really care whether they are additions or multiplications or in fact any other kind of computations. They could even be something highly complex which takes a large number of clock cycles in order to complete. The basic point of the data flow graph is that it just captures the dependency between the different computations, and the unfolding can then be applied at the level of the individual graph node elements. That is to say the A and B elements themselves without needing to worry about what kind of computations they are. On the other hand, in the original treatment of the parallel FIR filter, we did make use of some of the computations being multiplications and additions and so on. Whereas with unfolding, we just treat things as data flow graphs that can then be modified as required. So unfolding in some ways is a generalization of the idea of parallelism and can be applied in a lot of contexts in order to get benefits that allow you to get a better average sampling interval, especially in situations where the individual nodes that are involved in the computation are not well balanced and therefore not amenable to pipelining or retiming. And in such a situation, the unfolding transformation can allow you to make multiple copies of the hardware, which can then give you a much better average sampling interval.